Hello again, 8th grade. Well, we are going to continue on talking about earthquakes. I hope you had a good introduction to that yesterday. And now we're going to take a closer look at some of the details of the location and the causes of earthquakes, as well as the magnitude of them. Okay? All right, now I want to show you some things while we do talk about it. So I'm going to present my screen to you. All right. So I'm going to put something up here called a seismograph that we'll be talking about momentarily. Now, if you have your book, which I hope you do, please look with me on page 439. 439. Feel free to pause the video and get your book open to that page. Okay, on 439, I'm at 17.2, locations and causes of earthquakes. You know, we discussed back in chapter 16 that plate tectonic theory states that the Earth's crust is made of many large pieces called plates. Most plates are the size of a continent or larger. The plates are in motion. Their speeds have been measured by sensitive instruments using lasers and mirrored satellites. And today, the plates are moving very slowly, from just a few millimeters per year to 50 centimeters per year. Some plates carry continents with them. The plates collide at their margins, in other words, at their edges, and the margin of one grinds past or slides under the other. The shock waves caused by sections of the plates colliding and subducting, that means going under, are most likely the major source of earthquakes. Fold and fault block mountains, you'll recall those from the last chapter, are, in theory, a result of colliding plates, and a large portion of the Earth's volcanoes are found along the margins of plate boundaries as well, particularly divergent plate boundaries. The stresses of colliding plates produce cracks in the rocks of the crust called faults. If the blocks of rock on either side of the fault do not move, the fault is called being locked. That's very important. Moving tectonic plates continue to apply stress to the fault. The rocks will flex slightly, but as long as no slippage occurs, the fault remains locked. Eventually, because of the excessive stresses, the rocks along the fault surface fracture like a stiff rubber band, and the fault slips. As the rocks shift to their unstressed positions, the movement, called elastic rebound, produces waves of motion similar to the sound waves in the earth that radiate from the point of slippage. Often, slippage in one location of the fault increases the strain on the other locked portions of the fault, causing those sections to slip sometime later. These secondary earthquakes are called aftershocks. All right, now let's talk about seismographs and then the magnitude measured by something called the Richter scale. In chapter 13, we introduced earthquake scientists called seismologists. They use a special instrument called seismographs. You see a picture of one here. On the screen, on the left side, you'll see basically some old school looking seismographs. Now they're more electronic, like the one you see on your right. Early seismographs consisted of a large mass attached to a flexible supporting system. A light beam reflected off mirrors attached to the mass and traced a line on the rotating drum covered by photographic paper. If the earth moved, the recording drum and support moved, but the mass did not. The line on the paper thus became zigzagged instead of straight. The height of the zigs or zags showed the strength of an earthquake, especially of its waves. A seismographic recording is called a seismogram. Modern seismographs still use large masses, but the instruments sense and display the motions of the earth using electronic and digital components, including personal computers. Data is transmitted over the internet. So there's these seismographs all over the world. And we can collect their data almost instantly. For many years, seismologists have rated earthquakes by something called the Richter scale, named for a man named Charles Richter. The scale was based on the height of the seismograph trace produced on Richter's recording drum. The scale indicates the energy released, or the magnitude, of the earthquake. The Richter scale is not a linear scale, and this is important and something most people misunderstand. That is, an earthquake of magnitude 4 does not have twice the energy of an earthquake of magnitude 2. Instead, each change of 1 on the scale multiplies the energy by about 31.6. Thus, an earthquake of magnitude 3 has 31.6 times as much energy as a magnitude 2 earthquake. An earthquake of magnitude 4 has 31.6 times as much energy as a magnitude 3 earthquake, or almost 1,000 times as much energy as a level 2 earthquake. Modern instruments record earthquakes using different magnitude scales that are key to the type of wave received. Because the news media and the public have become accustomed to hearing earthquakes rated on the Richter scale, seismologists will convert the readings back to the Richter scale format before giving a public report. They will also average the readings from several stations to get the final figure. The Richter scale covers a wide range of earthquakes. An earthquake with a magnitude of just over 0 barely registers on a sensitive seismograph. People can feel earthquakes with a rating of 3 or more. A magnitude of 6 or more is potentially destructive. A quake whose magnitude is more than 7 is a major earthquake. A great earthquake has a magnitude of 8.0 or more. The Richter scale is not just a 1 to 10 scale, but is open-ended. The most destructive quakes usually have had a magnitude between 8 and 9. Calculations show that if an earthquake were a magnitude of 10 occurred anywhere on Earth, people around the world would feel the shaking. So, take a close look at this chart that you see on your screen. This is a scale, or it's a scale that shows the Richter scale. So notice its increase is exponential, right? To misunderstand that would be similar to misunderstanding exponents. So, for instance, you know, because you're in the 8th grade, that if you see 3 to the 4th power, you know, the number 3 with a small number 4 up above it. That does not mean 3 plus 3 plus 3 plus 3, right? Because that would be 12. No, what does it mean? It means 3 times 3 times 3 times 3. Well, that's a big number. I don't even know that number. 3 times 3 is 9. 9 times 3 is 27. Whatever 27 times 3 is. So it gets exponentially bigger. It's like that with the Richter scale. So there's a big difference between an earthquake that's a 7 and an earthquake that's an 8. Okay, even they do it in decimals, so they might say a 6.5 on the Richter scale or a 6.8 on the Richter scale. There's a huge difference between any of these numbers. So the greatest earthquake on Earth ever recorded was in Chile, which was a 9.5. That is so huge that it's hard to imagine. All right, well, that's an introduction to the locations of earthquakes, the causes, and then the magnitude and how we measure that on the Richter scale. All right, I'm going to go back to not presenting. All right. Now, look with me on page 440 at the bottom where it says Earthquake Richter Magnitudes. It tells you there via this graph that what number would cause what reaction. So if you'll notice, it says less than a 2.0 on the Richter scale is recorded, but it's not generally felt. Between a 2.0 and a 2.9, possibly felt by people. So that's the kind of earthquake that's happened near me before. I didn't happen to feel it, but some people did. If it's a 3.0 to a 3.9, it's felt by some people. 4.0 to 4.9, felt by most people. 5.0 to 5.9, damage to poorly built structures. 6.0 to 6.9, damage to well-built buildings. 7.0 to 7.9, major earthquake, serious damage. 8.0 to 8.9, great earthquake. extensive destruction near the epicenter, and greater than 9.0 massive earthquake, regional destruction, which means whole areas of a country can experience destruction. Okay, so that's an example. Now we're going to talk later about what is an epicenter and what is the focus, because no matter what the earthquake strength is, what you feel and the damage it would do would depend on how far away you were from where the earthquake originated, particularly the epicenter of the earthquake. The further away you are, the less damage there would be. And we're going to get on to that in our next lesson. So in our next lesson, we're going to talk about earthquake intensity, and then we're going to talk about focus and the epicenter. What does that mean? And how does that help us understand the nature and effects of earthquakes? All right, guys. Well, that's it for today. I'll see you guys later.